So first of all, thank you everyone for coming to today's colloquium at CQT. We had the pleasure of Professor Alexander Lvovsky to share with us some of his research findings. Now, Professor Lvovsky is actually quite well known in the field of quantum information theory. He is known for working on quite a broad variety of topics, and he has published many influential papers. Now, for just a quick introduction to his background, he completed his undergraduate in physics at the Moscow Institute of Physics and Technology, and he did his PhD with Sven Hartmann at Columbia University, studying optical effects in atomic gases. He has been a postdoc at Berkeley and also at the University of Constance in Germany, where he also started to lead a research group in quantum information technology. And since then, he has been leading research groups at Calgary and also in Oxford. Like I said, he's actually well known for various topics in quantum information, has even started applying machine learning, right, to quantum information experiments. And I hope we can actually hear some of that work in today's talk. So today we'll talk about topics about super resolution in optical imaging. Okay, and I'd like to pass the floor over to Professor Lvovsky.
Thank you. Thank you. Thank you for a nice introduction and also for inviting me. It's an honor and a pleasure. Well, that's the title. I guess I should comment why there is a dentist. It's a very old story. Back in 1994 or so, I was just a young graduate student in New York. I went to a dentist. The dentist was terrible. It was a complete crook. He like drilled all my teeth out for no reason. But he also liked small talk. And he asked me, what do you do? I said, I'm a graduate student. And what kind of research? I said, quantum optics. And then he said, oh, optics, interesting. In this case, I wish you one day to invent a new microscope. And I, of course, thought, what kind of nonsense? Quantum optics, parametric down conversion, photons, and then suddenly a microscope. But yeah, somehow I remembered it, and well, now we did invent a new microscope, and that's what I'm going to tell you about today. So that's the introduction to the group. There's the web page. We used to be a kind of hardcore quantum optics group, as Alex has said, but now we diversified quite a lot. So we do, in addition to quantum optics, we do machine learning, both quantum and classical aspects of it. We do optical neural networks and even a bit of robotics. The group is in the superposition state of Oxford and Moscow. So here are the pictures. They're seeing that there are many more people in Moscow celebrating New Year 2002 in this case. Right, now back to the subject of the talk. You of course know of diffraction limit, that all far field imaging methods are limited by diffraction on the imaging lens, on the objective lens aperture. The wider the lens, smaller the diffraction, but it's still significant. So if your source is a point, your image will be a point spread function. If you have two if you have two sources near each other, then their images will coalesce and you won't be able to tell that there are two sources and what the distance between them is. And basically, since invention of optical imaging, there's been a quest to enhance resolution of imaging methods, and one can classify them roughly into two groups. One group is near field imaging, where you have a probe that scans the surface at the in the near field, the direct neighborhood, and then there is no objective lens, no image, and therefore no diffraction limit. The second method is nonlinear optics, where you induce some kind of nonlinear optical effects in the medium to sort of get the different parts of the object to illuminate one by one, and then you can again enhance resolution. There was a Nobel Prize for one of these methods quite recently in 2014. But, well, all of these methods, both of these methods, are kind of invasive, right? So they involve direct active interaction with the object. And the question is, what if we cannot do it? What if the object is far away? What if it's untouchable? What if it's not? What if you cannot study it in the near field? Or what if it's it doesn't have nonlinear optical property or too fragile for nonlinear interaction, right? So it would be much more fun to invent an imaging device that would passively analyze the light coming from the object and yet extract and yet beat the diffraction limit. And one would think, of course, that this cannot be possible, right? Because diffraction limit, because this Rayleigh criterion has been invented 150 years ago, and nobody really challenged it since then. However, it turns out, and that was a revolutionary discovery that Monkey Tsang has made, who is in the audience now, I think, that turns out that yes, we can, but we have to fundamentally change the imaging method. You see, traditional imaging, what's traditional measurement, traditional imaging? Traditional imaging is when you may measure the intensity of light in the image plane as a function of transverse position. So intensity is a function of transverse position. But instead, we could do different measurements. We could, for example, measure correlation of field amplitudes and phases at different positions. And that would be a fundamentally physically different measurement. And as it turns out, you can extract more information from this measurement and beat the diffraction limit. So here's the idea of the method that Monkey has proposed. He said, well, this was very superficial what I said, right? Measure the correlation between amplitudes, but how can you actually technically do it? The answer is, what you can do is you have some field coming to you in the image plane. So what you can do is you can decompose that image into the Hermite-Gaussian transverse basis, right, into multiple transverse modes. And then you can measure the intensity in each mode. And then you can use the data to reconstruct the parameters of your object, and it can be various parameters, and eventually it can be full imaging as I'll show you. Yeah, some more. Here's a screen that shows intuitively why spatial mode, this method of spatial mode demultiplexing works. So the first statement is, suppose you have a source, for example, a star, on the optical axis of your instrument, of your telescope, right? And then you image it, and then you look at the intensity in the Hermite-Gaussian mode 0,1, right? So you filter just mode 0,1. This mode here. Here's a positive field, here's a negative field, and you look at the intensity just in this field. The image field is symmetric, whereas the mode is asymmetric. The scalar product between the two will be 0. So there will be 0 intensity in Hermite-Gaussian mode 0,1. Now, if we displace the object from the optical axis, then the symmetry will go away, and we will have some signal in Hermite-Gaussian mode 0,1. Right? If we have two objects, two stars, each of them will produce some signal. The two stars are incoherent with respect to each other, so each of them will produce some signal in HG01. As a result, you again will have some signal. And a precise analysis shows that this measurement, this, of course, the intensity here will allow you to measure the distance between the sources, and this type of measurement can be much more precise than via direct measurement. And this picture shows why it shows you the intuition why it is the case. So what if you have direct imaging? So there are two pictures of two slits in the lab. Well, this here is two slits. This here is one slit, but of course you cannot tell because the slits are too close. They're within the diffraction limit. So you cannot tell that this is two slits, right? So you have to distinguish, on the one hand, if you use direct imaging, you have to distinguish between this and this. If you have this spatial mode demultiplexing, then you have to distinguish between situations where you have no signal and a signal with some probability. It turns out that distinguishing between, well, no signal and a little signal is much easier than to distinguish between, well, a lot of signal and a slightly different lot of signal. Yeah, so intuitively, that's why this new method is more precise. And here, if you calculate the Fisher information, of course, you try to estimate the parameter, emit the separation of the two sources. Whenever you try to estimate the parameter, you can calculate the Fisher information associated with the measurement. And what you'll see is that if you use direct detection, then once the objects become closer, Fisher information becomes zero. That means that the uncertainty of your measurement becomes infinitely high. Whereas when you do this new method of Hermite-Gaussian demultiplexing, the Fisher information stays constant, meaning that in the limit of low separations, you can extract infinitely more information by means of Hermite-Gaussian demultiplexing rather than direct detection. So measurement can be infinitely more precise. So that's that's the idea. And once the idea was published, a lot of experiments have emerged. One point I'd like to make, one practical point I'd like to make is, well, how to make the mode sorter. So ideally, you want some kind of black box where you would have your image field as an input, and as the output, you'll have a bunch of fibers, each fiber containing light, containing the amount of light corresponding to its mode, right? So one fiber for 0, 0, one fiber for 0, 1, and so on. Boxes like this are actually possible to do. There is even a startup in France that fabricates these boxes, sells them. But they're quite, well, they're still quite imprecise, not very accurate, and technologically they are not easy to make. And we need a lot of modes for our experiments. So what we do instead is we choose an alternative solution. Namely, even though, as I said, it is very difficult to sort modes, it is quite easy to prepare Hermite-Gaussian modes. To prepare Hermite-Gaussian modes, it's enough to use either Fabry-Perot cavities that are slightly misaligned or a spatial light modulator. Yeah, and then you can use heterodyne detection with the local oscillator in the mode of interest. Heterodyne detection has this property that it only detects light in the mode of the local oscillator. So if you prepare your local oscillator in, for example, Hermite-Gaussian 0-1 mode, then the signal it detects corresponds to the content of the HG01 mode in the signal. Yeah, so you can simplify your experiment quite a bit. The problem is that if you do careful quantum analysis of this measurement, then you'll see that there's much less benefit in terms of Fisher information, which we'll go back to soon. But as I said, practically, this is much more convenient, and that's what we do, at least at the moment. So now I want to go to our first experiment that was done 6 years ago. Now, the experiment is, well, it was just aimed at sort of basic verification of man-case theory. So here's the scheme of the experiment. We have this is our microscope. It's a kind of toy microscope, meaning that our object is not really microscopic. It's a teaching. We borrowed this set of double slits from a teaching lab, and then we artificially used an optical system with a very small numerical aperture to sort of artificially reduce our resolution below the diffraction limit. Yeah, so this is our object, and now here we get our image field. On the other hand, the other arm here is preparation of the local oscillator. So here we used cavity to prepare local oscillator in Hermite-Gaussian 0-1 mode, then overlap the two and perform heterodyne detection. All right. So here are the parameters of the slit, parameters of the setup. One thing I should add is that we can do the experiment both with coherent and incoherent light. To do it with incoherent light, we'll have to move a white card in front of the slits, and then the image becomes incoherent. We can compare with direct imaging. And here are two sets of pictures. The first set of pictures with the iris fully open. So the diffraction limit does not really apply, and we get two nice images of the slit. If we close the iris to like 1 millimeter, then the diffraction limit applies, and you can see that the images coalesce. You cannot really tell them apart. So we work in this regime, and we apply this spatial demultiplexing technique, in this case in its primitive form, namely we detect mode HG01. So here's the result of this experiment. The left one is for coherent light, the right one is for incoherent light. So what happens is we move our, so in this case, it's a single slit, and the measurement is to determine the single slit position. So we move our slit around and we measure the signal. So when the slit is on the optical axis, then as we discussed, the signal is 0. As we move it off the optical axis, the signal becomes significant. When you move it too far, like away from the, so the image of the slit no longer overlaps with mode 01, then of course we lose the signal completely again. But then, you know, by the signal here at the central area depends quite strongly on the deflection, so we can actually evaluate the uncertainty of the slit position very precisely, up to about 1,000th of the Rayleigh limit, right? So if our Rayleigh limit here is a millimeter, we can estimate its position up to like a micron, and in case of incoherent light, up to 10 microns, just because light is weaker. So that was a single slit. If you try to measure the separation of the two slits, then you get a similar result. So again, if you work with a single slit and position that on the optical axis the signal is 0, so remember we had this sample with 4 slits. So what we do is we just align the setup for each of these 4 slits, and we see that the signal gets bigger and bigger as expected theoretically. So that was the basic theoretical confirmation of Mankey's work. At the same time, a number of other experiments appeared, notably one from Singapore, from the host of our today's seminar. I mentioned heterodyne detection already. As I said, heterodyne detection is convenient experimentally, but theoretically not as beneficial. So here we did a collaborative work with Mankey where we analyzed this in detail. So basically this slide explains why heterodyne detection doesn't work as well as does single photon detection. So what does heterodyne detection do? It measures the quadrature of your electromagnetic oscillator. Yeah, so it gives you, if you have a single distribution in the vacuum state, right? So if you have a single emitter position on the optical axis, so that Hermite-Gaussian mode 01 is in the vacuum state, then the quadrature distribution that you see looks like this, right? So it's a broad distribution, somewhat broad distribution. If you have now 2 emitters that are separated, right? So the signal is non-zero, then well, the state of mode 01 is thermal, very weak thermal state. That means it's very close to vacuum. So the distribution of your quadrature is quite similar to this. It's just slightly broader. Yes, you have to distinguish between this distribution and this distribution. Now, remember I showed you this picture here. So I said for direct imaging, you have to distinguish between like some distribution and slightly different distribution. Whereas for Hermite-Gaussian single photon detection, you have to distinguish between no signal and some small signal. Well, here in the case of heterodyne detection, you again need to distinguish between some distribution and a slightly broader distribution, right? And that's why for weak signal, the benefit of heterodyne detection sort of disappears, as becomes as poor as for direct imaging. So here in this picture, we plot the per photon Fisher information. for various methods, namely for direct imaging, right? For photon detection. So this blue and green line is what I've shown you before. But in addition to that, I show you here a bunch of red lines, which correspond to heterodyne detection with different number of photons per mode. And you can see that indeed, if the number of photons per mode is small, if the source is relatively weak, then there is no advantage. So you get even less special information than with direct detection. Whereas when sources are relatively strong, right, when you have hundreds of photons per mode, then there is advantage with respect to direct detection. And one can, again, intuitively understand where this advantage is coming from. As I told you before, we need to distinguish between, well, the vacuum state distribution and thermal state distribution. But if our source is strong, then the thermal distribution is significantly wider than the vacuum state distribution. Yeah. So because these two distributions are significantly different, so even for small separations, they become significantly different, then you can extract more information and measure your separation of the emitters more precisely. So that was this theoretical work. Now I'd like to tell you how to extend this idea of spatial mode demultiplexing to full imaging. You see, the experiments so far, the great majority of the experiments so far, I think all of the experiments, involved basically estimating individual parameters of the object. So it was not really imaging, it was just parameter estimation. And what we have contributed now is extension of this method to full imaging. We have shown that one can in fact get full information about, or more or less full information about your object in the form of an image. So here's the theoretical idea that was proposed in this paper. Of course, it's hard to say now, like, you know, who first proposed this, because it's relatively straightforward. But here we analyzed it in this paper of 2016. So what we said, look, suppose we use not only Hermite-Gaussian mode 0, 1, like we did before, but measure all the modes one by one by means of our mode filter. Right, so we have our heterodyne detector. The heterodyne detector produces photocurrents. What is this photocurrent equal to? It turns out that the photocurrent essentially is proportional to the mnth moment of the source field. Yeah, so if we measure the mnth Hermite-Gaussian mode, our signal will be proportional to the mnth moment of the field. Now, as we know from statistics, if we know all the moments of a certain distribution, we can use these moments to reconstruct the distribution itself. So that's the basic idea. Of course, in practice, you cannot measure all the modes. You can measure only some of the modes, but still you can reconstruct the image. Now, this set of equations here are for the coherent case, when the source is coherent and you measure the amplitude of Hermite-Gaussian modes. If the sources are incoherent, then you have to measure the intensity. The phase contains no information. You have to measure the intensity of Hermite-Gaussian modes. And the mathematics becomes slightly different, but only slightly, because still you have the moments, you obtain the modes of the distribution, but only the even moments, not the odd moments. You cannot obtain any information about the odd moments. What does it mean in practice? In practice, that means that if you try to reconstruct the object from these even distributions, from these even moments, in addition to the object itself, you'll get ghost images. Yeah, you'll get, in addition, you get these 4 additional images that are sort of mirror reflections of your object with respect to the optical axis. How can one address it in the experiment? Of course, you don't want the 4 images to be superimposed, but if you displace your object slightly sideways, then you'll get the 4 images separated and you can make out your object clearly. So that's one approach to address this ghost image issue. Another approach that was proposed by Monkey again is to use, in addition to Hermite-Gaussian modes, use superpositions of Hermite-Gaussian modes. So for example, in addition to mode 5, 5, we use a superposition of 5, 5, and 6, 5, and 5, 5, and 6, 6, and so on. So now these modes are not symmetric, and they, if you measure the intensity in these modes, you can actually address this problem of parity. You can eliminate ghost images. Of course, the shortcoming of this method that you have to do is that you have to do more measurements. Now, this plot shows the theoretical resolution that you can obtain as a function of number of modes. TM means the transverse electromagnetic mode, same as Hermite-Gaussian. So the more modes you use, the better resolution you obtain. The dependence is approximately inverse square root, right? So if you use 20 modes, and 20 is entirely realistic, as you'll see, then the resolution enhancement is by about a factor of 3, which is a big deal. In current microscopy, even like, enhancement of resolution by a factor of 1.2 would be considered a major event. And here, theoretically, we can have a factor of 3. So here's an proof of principle experiment where we have demonstrated this. The setup looks almost like the one of 2016 with the following differences. First of all, we no longer use a slit because we want a diverse set of objects. So we no longer use this laboratory slit. Instead of we use spatial light modulator, specifically a digital micromirror device to form various objects. That's point number one. Point number two is that we no longer use a cavity to make our local oscillator modes. Instead, we use a liquid crystal spatial light modulator here in the local oscillator channel, again for the sake of diversity, so we can easily switch between various modes. Otherwise, we still perform heterodyne detection, measure signal in various modes, and then reconstruct. Well, this is our object. Our object are various logos of our university. We divide logos into small squares of like 21 logical pixels. Each logical pixel is in turn 10 physical pixels on the DMD screen. We display those subframes one by one, like it's shown here. For comparison, here we show the point spread functions both in the intensity and amplitude, work in the coherent regime. So we have to compare this with this. And you can see that if your point spread function looks like this, then you cannot really distinguish the letters. Now, an important point that I have to make is that, remember I told you how we reconstruct the image. We reconstruct the image by collecting higher order moments of our image field by detecting in various Hermite-Gaussian modes. And then we can mathematically reconstruct the object. The problem is that this mathematical reconstruction assumes that everything absolutely perfect, right? That our Hermite-Gaussian modes are perfect, that our point spread function is perfectly Gaussian, that there is no dust, no aberration, and so on. Everything is perfect. As soon as something becomes imperfect, everything falls apart. Now, why does it fall apart? It falls apart because signals in different modes, here you can see signals in different modes in this plot here, are very different in order of magnitude. It can be like 5 orders of magnitude different, meaning that if you have a small error in a signal associated with a low order mode, then your higher order modes become useless, right? They fall off completely. So yes, so this simple mathematical approach cannot be used. Instead, what we use is a neural network. Namely, we construct this neural network that takes in photocurrents. So the input of the neural network is the photocurrents associated with different Hermite-Gaussian mode. And as output is the reconstruction, the object reconstruction, right? So the purpose of the network is to reconstruct the image, the object, from heterodyne photocurrents obtained in different Hermite-Gaussian modes. And well, here are the parameters of the network. 2 points I want to make here. First of all, that for training, we use like 20,000 various complex images. So various complex subtrains containing like lines, little squares, and so on. So we have like this huge training set that is used to train the neural network. The second point is that the label that we use for training is not an object itself, as one would sort of naively do, right? To want to reconstruct the object. So as the label for your training, you would use the object itself. But turns out to not work very well, because if you try to do that, that means that you are trying to extract features of the objects that are physically not there, right? That the physical signal does not contain, and yet you try to make the neural network to extract these features. As a result, you overfit the neural network. So it doesn't work well. So instead, what we do is we use slightly smeared object as our training label. Yes, so we actually use theoretical HGM reconstruction for the label, and then we do get nice results that are shown here. So this is sort of the main result that I wanted to demonstrate. This is our original logo of the university. This is the image obtained by direct imaging, and this here is the image obtained by our method. You can see significant resolution enhancement. And in fact, you can quantify this resolution enhancement by plotting, by imaging pairs of parallel lines. And you can see that if you do direct imaging, then you can only distinguish these two lines. Whereas if you use our method, then you can distinguish these two lines. So you can enhance the resolution by a factor of 2. In fact, we can even plot the resolution enhancement as a function, again, of the number of modes used. And you can see that we are almost as good experimentally as expected theoretically. Now, the results I showed you previously were for coherent light. Similar results can be obtained for incoherent light. These are preliminary results, not yet published. So basically what we do for incoherent light, like we simulate incoherent light by illuminating our logical pixels on the object one by one and measuring them separately, right? So in this way, you can be sure that the pixels are not coherent with each other. So you can simulate incoherence, right? And then again, you can see that the resolution is significantly enhanced. And then this final set of imaging is for confocal microscopy. So if in previous experiments we illuminated the object broadly, here we illuminate the object by a tight focal spot. And well, and again, you see enhancement, right? So this is the label, this is the Hermite-Gaussian microscopy, and this is direct imaging. So similar level of resolution enhancement for confocal microscopy. So confocal, so basically it means that our method is compatible with confocal microscopy. Confocal microscopy increases resolution, right, with respect to simple direct imaging, but then on top of it, we can throw our method and further increase the resolution. Now, there is an elephant in the room, of course, the quantum advantage of our method. Does our method possess quantum advantage? You see, we do not do photon counting, right? We basically in our experiment we have as many photons available as we need. Whereas all these theories, Monkey's theory in particular, counts photons very rigorously. It calculates Fisher information per photon. Yes, so this is and then shows the advantage. And that's very important. That's a key feature of that theory, because you see, if light did not have quantum nature, if light were classical, then there would be fundamentally no diffraction limit at all, right? Then no matter how much your image is smeared, what you could do is you could apply deconvolution and reconstruct the object precisely. You cannot do that exactly because the light has quantum nature and because it and because of the resulting shot noise. Yeah. So as I said, we don't do photon counting in our experiments. And then the question is the advantage that we observe really rigorously, right? And then how would it behave in a low photon number regime? Is it quantum optimal at all, right? Can we do better? So here, so one of our graduate students, Jose Da Costa, who graduated now and went to Harvard, used quantum estimation theory to answer these questions. I should say that also related work here, one of them again by Mankey. So here's what he did. He took n incoherent sources, placed inside a circle of some diameter which is comparable to the size of the point spread function. Yeah, and then he used the sources are incoherent, and he used this Hermite-Gaussian microscopy to perform intensity measurement, right? And he treated this as a parameter estimation problem. So he has 3 n parameters, namely the position of each source and the intensity. And he then computed the quantum Fisher information associated with this measurement for different positions of objects. So it's a numerical study. He always had 5 point sources, right? And well, he assumed a constant photon number, and there are different objects all satisfying this condition. So all of the objects are like 5 sources positioned within this circle of a given size. He averaged the quantum Fisher information over 30 various objects and plotted the results. He used 2 figures of merit. One is the quantum Fisher information. So, well, he calculated the Fisher information actually because there's many parameters, and Fisher information becomes the matrix, right? So what he do to make it a single parameter, he took a trace of this matrix, and that of course that can be used as a single figure of merit. The higher Fisher and the higher the trace of the Fisher information matrix, the more precise your reconstruction, right? So this is one figure of merit, but it's quite abstract. So it's not doesn't tell you exactly how much resolution is enhanced. So he also used here another technique and then another figure of merit that is well, resolution enhancement, the numerical resolution enhancement. Namely, he said, okay, so with our method and with our numerical aperture, we obtain a certain Fisher, certain trace of the Fisher information, a certain K. Now, with classical direct imaging, we would of course also obtain some Fisher information, a different K prime, right? This Fisher information for direct imaging would be poorer than that with our method. But then as we increase the aperture, then the direct imaging would give us more and more precise picture, so a K will increase. So the question is, at which numerical aperture would we obtain, at which numerical aperture NA prime would a direct classical measurement give us the same Fisher information as our method with the numerical aperture NA? Yeah, so you can compute NA prime, you know your NA, you divide the 2, and this ratio of apertures gives you a figure of merit, gives you like direct resolution enhancement of the method. And well, here we plot this resolution enhancement as a function of the diameter of the image. Remember, the object is a bunch of point sources located within a circle. So here we plot resolution enhancement as a function of the source diameter. And here's a bunch of curves, so I'll go slowly through these curves. The blue curve here is direct imaging. Of course, by definition, the direct imaging has no resolution enhancement over itself, so it's always 1. The red curve here is the quantum limit, quantum Fisher information. Yeah, and you can see that the quantum Fisher information is no longer constant because it's a more complex task than, because it's imaging is more complex task than object separation. So actually, well, the Fisher information, the the Fisher information is not constant, but more important, but what's plotted here is not the Fisher information, is the resolution enhancement. You can see that the resolution enhancement grows as the object becomes smaller and smaller, again, as expected. Now, there are various experimental methods, various variants of Hermite-Gaussian imaging. One is direct mode sorting. This is this green curve here. You see it performs quite poorly. The reason is those ghost images that I told you about before, right? So if you do simple mode sorting, then you get ghost images. You cannot distinguish those ghost images from the actual object. So the reconstruction is not accurate. The brown curve here is the displaced mode sorting. So here, as I described, you can displace the entire object aside from the optical axis, and then your ghost images will be in different, the object reconstruction and the ghost images will be in different quadrants. So you can now make out the object. The performance is much better. The yellow curve here is interferometric mode sorting. So here we apply this method of additional, we use additional Hermite-Gaussian modes, namely the superpositions of Hermite-Gaussian modes, to eliminate ghost images. And you can see that the performance is even better. Now it actually approaches the quantum limit. And finally, the final curve here is the purple curve. So here we again use this interferometric mode sorting, superpositions of Hermite-Gaussian modes, but now in the regime of quadrature detection. So we don't assume that we have a black box that sorts modes. Instead, we use a heterodyne detector. As we discussed, heterodyne detection doesn't work as well. Has disadvantage in terms of Fisher information, and here we see this disadvantage. However, there's still the performance is still higher than direct imaging in the case of small object diameters. So, well, here you can see the actual reconstruction. So if this plot is simply the resolution enhancement, here is the actual reconstructions of objects using different methods. Now, these figures are quite busy, so I'll go slowly through them. The white crosses here, you see the 3 white crosses. The 3 white crosses are the actual objects, and well, their positions are the same in all 4 figures. The difference between the 4 figures is the different sizes of your object, right? So the left figure is when the size is small. The right figure is when the size is big. The blue point here is direct imaging. And you can see when the size of the object is big, the direct imaging is actually quite precise. Here, I think you cannot see it because it's superimposed with the object point. But you see that for large objects, direct imaging is quite precise. But as your object becomes smaller and smaller, direct imaging fails completely. You get just a single point somewhere, at the average location. Now, green points here are direct imaging. And green points here are mode sorting, regular mode sorting. And you can see the ghost images. So in addition to points, say here, here, and here, you also get the ghost images like here, here, and so on. So you get a bunch of ghost images, and these damage your reconstruction quite a lot. You cannot really tell where the object is and where the ghost image is. Now, the red pictures here are displaced mode sorting. So for displaced mode sorting, you see that the reconstruction becomes quite accurate with, well, sometimes artifacts being present. And then finally, the yellow pictures correspond to this interferometric mode sorting with superpositions of Hermite-Gaussian modes, and you can see that the reconstruction is more accurate. more accurate. Now it contains no artifacts, so it fulfills the purpose. So basically what these results show is they justify our method, right? They show that even though in our specific method we did not use photon counting, if we did use photon counting, if we did have a limited number of photons, still this Hermite-Gaussian imaging would provide better quality results than direct imaging. So I've come to the conclusion of the talk. So here's the list of points that we've achieved so far. So again, we have implemented this new imaging technique that achieves super resolution with a number of advantages compared to other super resolution methods. Namely, it only involves passive observation of the light coming from your object. It only involves linear optics, linear optical methods, and it works in the far field, right? And that's a unique feature of the method. We've demonstrated the validity of our technique for both coherent and incoherent light, and we validated our technique through quantum figures of merit. So that's what's achieved so far. Now, what needs to be done to make it sort of a universal microscopic technique? There are two goals that need to be achieved. First is that, as you've seen, our experiment was sort of a toy experiment. It was with a toy object, not a truly microscopic object. So we need to extend it to proper microscopic object, meaning that well, we need to figure out how to construct a training set differently. You see our training set now contained like 20,000 objects, which is a lot. We won't have it in real microscopy, so we'll have to figure out a different approach. Yeah, but we have ideas how to do it. And the second important point is that, well, we use heterodyning. And as we discussed, heterodyning has disadvantages, but more importantly, it is not universally suitable for microscopy because what's traditional microscopy or traditional astronomy? In microscopy, the signal is fluorescent signal. It's like, hundreds of nanometers. In astronomy, again, the signal is broadband. On the other hand, heterodyne detection can only deal with narrowband signals, maybe a gigahertz or a few gigahertz, but not more. So that means that we have to now apply proper mode sorting, proper like black box mode sorting that I told you about to our approach. And again, we believe it will work together. The two methods will work together nicely, but we have to demonstrate experimentally. These are our tasks. If you want to join the task force and try working on these techniques, then actually we have a postdoc position now open. So please let me know and join the group. Thank you for listening.
Okay, thank you. Thank you, Alex. It was a very nice talk and, very pedagogical approach to the problem at hand. Now, for the audience who are online, if you have any questions, you can type that into the chat, right? And I'll try and read those questions out for, and we'll go through those questions that you have. But in the meantime, I would just like to start, the question and answer session by asking a few questions, just to try and understand, the challenges in the experiment a little bit better. So Alex, you said that, when you were working with this experiment, you needed to increase the number of photons per mode. And then when you had, a sufficiently large number of photons per mode, you had an advantage over direct imaging, especially when the objects were very close together. So how does one actually understand this in an actual experiment? Like, how much power do you need to apply in this experiment in order to get that advantage?
Well, we didn't study this experimentally, right? Well, we did some numerical studies, but experimentally we just, we had our laser, which is a few tens of milliwatts, and we did not vary the power and see how poor the reconstruction becomes when we reduce the power. We did numerical studies, and numerical studies just showed that some of these I showed you in the talk. They show that that the Hermite-Gaussian microscopy has the advantage versus direct imaging.
Okay, okay. So it means that there's some room here where we could actually reduce the power that's involved in the experiments, because I can imagine that there will be certain kinds of samples that are sensitive to
That's
the
right.
power level. Yes. Yeah. Could I ask you to hazard a guess, like, you know, how much you could reduce the power and still get a useful signal?
Well, I think a few thousand photons. With a few thousand photons per frame, you like, well, we actually, you know, I don't have a picture here, but if you look at the supplementary to our PRO paper, we show that even if we reduce the number of photons to even a few thousand per subframe, then you still can make out a decent quality image.
Okay, okay.
And the subframes are quite, you know, quite complicated here. I'll show you. So this is an example of a subframe. Yeah, so that's what you need.
Okay, all right. Now for the, I want to switch gears a bit and ask about the neural network, because that's actually quite intriguing. You mentioned that you needed about 20,000, you know, training sets or training samples to train the network.
Yes.
And that's for, will you say that's for a relatively simple object? And so
Well, there is an, that's what a typical element of a training set looks like.
Okay. So if you were to try and do real imaging, how does it, I mean, how many more, you know, training samples would we require?
Right. So actually, incoherent imaging is easier to do than coherent imaging, because for incoherent imaging, we can do pixels one by one, right? So we could do just a single pixel. We can move it around. For each position of the pixel, we can extract the currents, and then for other incoherent objects, we just add these currents together. Right.
Okay.
So yeah. So for incoherent reconstruction, it's actually easy. For coherent reconstruction, it's more complex, because, well, there you would need to add photocurrents, and then it becomes, in practice, it becomes more difficult. For coherent object, what we thought of doing is we could, you know, if we have some kind of rough object with arbitrary structure, then we could move this object around, we could rotate it, and so on, and that would give us, you know, thousands of different images that we could train on.
Okay, thanks. Yeah, maybe I can, you know, ask the audience now if they have any questions. Maybe first of all, let's ask the online audience. Does anybody want to ask anything? Okay, everybody seems very shy today. How about our friends who are here? Anyone who wants to ask any questions? Yeah.
Thanks, Alex, for the talk. So, can you hear me? Can you hear me?
Not very well. Maybe you can come closer.
Okay, so thank you for the talk. I just want to ask, because like you've been using Hermite-Gaussian modes in this all the experiments and simulations and that, but is it possible to use other mode basis, like maybe Zerniker modes or Lagrange-Gaussian modes?
So the question is, as I understand, can one use different bases, for example, like Gaussian modes? The answer is probably yes. We didn't investigate this, but I see no reason why not. But if you take, for example, there was a paper by Boyd's group, numerical, and it was numerical modeling. They didn't use exactly the same technique as us, so they also did mode sorting. But then the reconstruction was done by means of deconvolution in different modes, and they used Zerniker modes. So a very different set of modes. I think these Zerniker modes are more suitable for a top hat aperture. So and Hermite-Gaussian modes are optimal for a Gaussian aperture, whereas Czerny modes are more suitable for, well, for cylindrical apertures, and of course most microscopes do have a cylindrical aperture. So yes, one can use different sets of modes. I don't believe there would be dramatic advantage though.
Okay, any other questions? Okay, looks like everyone's quite shy. Maybe I ask Alex, you know, is there plans to try out this technique on, you know, actual samples, like maybe biological samples of any kind?
Yes, so the plan right now is to, well, is to try two kinds of samples, namely a reflective microscopic sample. With the reflective sample, we can still use heterodyne detection, and then a fluorescent sample. With the fluorescent sample, we need to use mold decomposition. And then once these are done, so once we've elaborated the mold decomposition technique, the next step would be biological samples.
Okay, okay, great. Yeah. Well, I guess last call for questions. Anyone?
Just
yeah, Angelina, go ahead.
Thanks. Just to follow up on that, if you mentioned that you want to transition to something like dynamic or biological samples, and you use such a large training set at the moment to train the network, how realistic or short term do you view that transition to be? It looks really challenging to perform such a training on something as complex and very varying as a biological sample.
Right. So these experiments here, the incoherent, these experiments here, the incoherent images. With the incoherent images, the training set can be much smaller, right? Because what we did here is we simulate incoherence by printing logical pixels one by one. Yeah, and then the training set would just consist of, well, the experimentally acquired training set would consist of, pixel here, pixel here, pixel here, and so on. So it would be on the, single pixel at different locations. Then from these experimental data, we would produce a simulated training set consisting of multiple combinations of these pixels. Yeah, we would still train our network on a large training set, but what we acquire experimentally is much smaller, right? And that, of course, is much more doable, right? You take a single fluorescent source, you move it around in your view field, you calibrate your microscope with this single source, and then you can reconstruct images.
Okay, thank you.
Okay. We do have a question from the online audience. It's from Ranjiv Nair. So Ranjiv is asking if you already have a mode sorter in the works, and how many modes are you able to sort at the moment?
No, we don't. So this French company, Nicolas Treps, I think they can sort up to about 10 modes, so single digits, with the fidelity of 90-something%. So it depends, of course, on the particular combination of modes. So it doesn't work as well as heterodyne detection, but it works to an extent sufficient to demonstrate significant resolution enhancement.
Hey.
But not in our lab yet.
Okay. Okay, Alex, thank you very much for taking the time to join us and share with us your findings today. I think the audience definitely learned a lot about what you're working on and the techniques that you're applying on for super resolution imaging. So let's like to thank you again, and maybe everyone in the audience can also give a thumbs up to Professor Lvovsky for taking the time to join us. Thank you, Alex.
Thank you very much. Thank you for inviting me. It was great to talk to you.